Warning: do not copy. Our programs are covered by registered U.S. copyrights. They may not be duplicated or copied. Willful infringement constitutes a felony punishable by fine and imprisonment. Civil remedies include statutory damages of up to $50,000 per offense, plus plaintiff's attorney's fees.
Operational Amplifiers Explained. Part 1. General Amplifier Concepts. Today, electronics controls more aspects of people's lives than ever before. The design of integrated circuits has enabled them to become smaller, even as they have become more powerful.
This series will explore an important component found in electronics today, the operational amplifier, more simply known as the op-amp.
This series will provide an overview of linear op-amps.
You'll see how they can be used to produce inverting and non-inverting amplifiers.
You'll have a chance to analyze and work on actual op-amp circuits. The first part will focus on general amplifier concepts.
Using a universal amplifier model, basic characteristics will be examined, including input resistance, voltage gain, output resistance, and frequency response. Let's get started.
The op-amp is probably one of the most useful amplifier circuits in electronics today. Although op-amps were first developed 40 years ago utilizing vacuum tubes, today they are constructed primarily as linear integrated circuits. The outputs of linear circuits are directly proportional to their inputs.
Op-amps are commonly found in audio mixing boards, for example, where they enable the combining of audio signals.
Variations of op-amps called instrumentation amplifiers are used in process controllers to regulate many different aspects of manufacturing. Here, the consistency of paperweight is being calibrated.
Op-amps play a key role in the interfaces which allow this robot to function.
Before going into specific characteristics of op-amps, let's review some general amplifier theory.
There are several characteristics that affect how amplifiers are used and how they interface with other devices.
Any amplifier can be considered as a unit, regardless of the types of devices used in its construction. It may have only one active device, such as the single-stage preamplifier, or be multi-staged, comprised of many devices, as in the case of this stereo amplifier.
Amplifiers may be any one of three basic types: voltage, current, or power. Op-amps are the voltage type. Let's explore the parts of this universal amplifier model. The amplifier functions take place within the dotted line box. The two voltage input terminals on the left, designated V-in, connect the amplifier to a signal source. Let's add it to the diagram to get a better idea of how the signal is provided. In this series, a sinusoidal signal source will primarily be used, designated Vs. The signal source treats the quantity Rin as its load. Rin stands for the input resistance of the amplifier. You may also see this quantity referred to as input impedance, symbolized by the letter Z. The input resistance of an amplifier is the equivalent resistance calculated looking into the input terminals of the amplifier. The value of Rin is dependent on the type of amplifier being analyzed.
Let's see why the input resistance is so important to the amplifier. Consider this circuit diagram. Notice that there is a source voltage of 200 millivolts. There is an equivalent source resistance labeled Rs of 1,000 ohms. The amplifier has an input resistance of 100 ohms. Using voltage division, the calculations show that of the 200 millivolts, only about 18 millivolts, designated Vin, appear across the input resistance of the amplifier. This means that of the 200 millivolts you started with, only 18 millivolts are available to be amplified.
Let's look at another example with Rs and Vs remaining the same. The input resistance now is 10,000 ohms. Your calculations will show that the amplifier has at its input about 182 millivolts to amplify. You can see that by looking back at the earlier example, the greater the value of the input resistance, the greater the value of the input signal to the amplifier.
Using waveforms, you can see that decreasing values of input resistance cause the input signal to decrease. When this happens, the amplifier is said to be loading down the source. As a rule, voltage amplifiers such as the op-amp incorporate as large an input resistance as possible. The ideal voltage amplifier has an infinite input resistance. Let's use an oscilloscope to examine some actual amplifier circuits and watch the effect of input resistance on the signal source. The amplifier on the right has a low input resistance. Without connecting the signal source to the amplifier, you can see on the oscilloscope screen that it has an output of 2 volts. This is because there are 2 divisions of amplitude at 1 volt per division. Connecting the signal source to the input of the amplifier and turning on the signal source causes its voltage to drop. This means that the amplifier has loaded down the signal source, resulting in a reduced input voltage to the amplifier.
Now look at the amplifier on the left. It has a high input resistance. Let's connect the same 2-volt signal source to the input of this amplifier. Notice that the signal source voltage does not change as severely as with the previous amplifier. The amplifier with the high input resistance does not load down the signal source as much as the amplifier did with the low input resistance.
Let's go back to the amplifier model and examine another important quantity. It's called voltage gain. It's labeled AV. This represents how many times the input signal Vin will be amplified, creating an enlarged voltage. Generally, when dealing with a voltage amplifier, it is desirable to have the gain as large as possible. An ideal amplifier has a voltage gain that is infinite.
The last basic quantity to get acquainted with on the amplifier model is the output resistance, Rout. Output resistance is also referred to as output impedance, Zout. This is the equivalent resistance seen looking back into the amplifier's output terminal. The importance of the output resistance lies in the ability of the amplifier to deliver a signal to a load designated RL.
Let's insert some values to see the interaction between Rout and RL. In this example, a signal has been amplified to 3 volts. The 3 volts is applied to the load resistance of 200 ohms through the 2000 ohm output resistance. Calculations show that of the 3 volts available from the amplifier, only 0.27 volts actually appear at the load. On the other hand, if the output resistance is decreased to 10 ohms, after performing the calculations, you'll find that the voltage appearing at the load will increase to 2.86 volts. Here, the load voltage is indicated on the model.
Amplifiers are designed so that the output resistance can be kept as small as possible. An ideal amplifier would have an output resistance of 0 ohms. The higher the output resistance compared to the load resistance, the smaller the voltage will be. Here, the amplifier is said to be loaded down. The important task of an amplifier, then, is to drive a signal into a low-resistance load. High-resistance loads are generally not a problem to a voltage amplifier.
Let's explore some real effects of output resistance in the same two amplifier circuits. The circuit on the right has a high output resistance, and the circuit on the left a low output resistance. The right amplifier has an output voltage of 1 volt peak to peak, which is 2 divisions at 0.5 volts per division. The oscilloscope looks like a very high resistance load, which, remember, will not be a problem to a voltage amplifier. But now notice that when a 100 ohm load resistor is connected to the amplifier with the high output resistance, the output drops considerably. This means that the amplifier is not capable of driving a signal into a load as low as 100 ohms. In this case, the amplifier is severely loaded down.
Now let's look at the amplifier on the left with the low output resistance. Here, with only the oscilloscope connected, there is also an output voltage of 1 volt peak to peak. When the 100 ohm load resistor is connected to this amplifier, the output voltage changes only slightly. This means that in order for an amp to drive a low resistance load, it must have a very low value of R out.
There is one more amplifier aspect to consider that is not represented on the model. It's called the frequency response of the amplifier. This will indicate which frequency signals the amplifier is capable of handling at the desired gain. Typically, frequency response is represented by this type of curve. Perhaps you've seen one like it for a tape deck or an amplifier in an audio magazine. The curve shows the voltage output signal on the y-axis versus the signal frequency on the x-axis. It is assumed that the input signal is the same voltage at all frequencies.
Taking a closer look at the curve, you can see that at high frequencies, the output voltage decreases, even though the input voltage is constant. Similarly, on the low frequency end of the curve, even though the input voltage is the same as everywhere else on the curve, as the signal frequency increases, the output voltage increases. This occurs until a certain frequency is reached.
This variation is due to the fact that capacitors are used to couple the signal or bypass signals in the amplifier. Because coupling or bypass capacitors are not present in op-amps, they do not have this low frequency characteristic. The op-amp will amplify uniformly down to and including DC or 0 Hz signals.
Notice the middle portion of the curve. You can see that the output voltage is relatively constant. This region is called the mid-band region. The mid-band region is the band of signal frequencies that the amplifier will be effective in amplifying with a constant gain. Remember, an ideal amplifier is capable of amplifying a signal of any frequency. Its frequency response curve becomes a straight line.
Now you've been introduced to some general amplifier characteristics, but along the way you've seen some of the characteristics of an ideal amplifier. Let's put the ideal amplifier characteristics on a chart and compare them with those of an op-amp. You'll begin to see why op-amps are so versatile and popular today. The input resistance of an op-amp is not infinite, as would be desirable in an ideal amplifier. The typical op-amp has an Rin range of megohms. However, when compared to the resistances found in the circuit to which the amplifier will be connected, this is often large enough to be considered infinite.
The ideal amplifier would have an infinite voltage gain. The op-amp typically has a gain that multiplies the signal by hundreds of thousands.
The output resistance of the typical op-amp is often under 100 ohms. This comes relatively close to the ideal output resistance of 0 ohms when compared to most load resistors to which it would be connected.
The typical op-amp has a frequency range of only 10 Hz. Although this is poor when compared to the infinite frequency response of the ideal amplifier, you'll see in a later part how this can be improved.
You can see that with characteristics that approach those of an ideal amplifier, the op-amp is an extremely useful circuit designing tool. Let's stop here and review.
In this part, general amplifier concepts have been covered. To summarize, a general voltage amplifier should have a large input resistance, a very large voltage gain, a small output resistance, and a mid-band range that is compatible with the signals it will be receiving. The capabilities of an op-amp go way beyond these and are comparable to an ideal amplifier.
In the next part, the various functional blocks of the op-amp will be explored. You'll gain a better understanding of why each of these blocks are used.